Good afternoon, everyone. I am Dr. Ritish Kumar, Assistant Professor, Department of Electronics Communication Engineering, Kumar Engineering College, Ghaziabad. So, in today's lecture, we will discuss the subject microwave and radar engineering, in which we will cover the topic of microstrip line, which is the most important topic of the of this subject. Let's begin. What is the microstrip line? So microstrip line is nothing but a transportation media through which RF signal or electromagnetic wave uh, passes from RF source to load. So there are various kind of microstrip line based on the structure. We we can categorize in the form of geometrical and mode. So in the geometrical point of view, we can have two types of transmission line. The first one is the multi-conductor based transmission line and single conductor based transmission line. And based on the mode characterization, we have a different kind of transmission line which has TEM mode, non-TEM mode, etc. So non-TEM mode, we have TE mode, TM mode, TEM mode, etc. So we will discuss later. In this topic. So geometrical point of view, the first one is a multi-conductor transmission line, which for an example such as coaxial cable, twin lead line, parallel plate line, and strip line, etc. So you can see here, this is a cross-sectional view of a coaxial cable, where we have the inner conductor and outer conductor. So inner conductor here, simply we can say we have more than one conductor. The first one is the inner conductor and outer conductor. So we can characterize this transmission line in the multi-conductor transmission line, while in the case of single conductor, we have a transmission line as a waveguide. So you can look at here, this one is a waveguide which is made only by using a single conductor. That's why we call this transmission line as a single conductor based transmission line. Apart from it, the other one, the transmission line based on the mode, is non-TEM mode, as I discussed earlier. TE mode, TM mode, and HEM mode. What is the meaning of TE mode? TE mode is the transverse electric mode, while the TM mode is transverse magnetic mode. As here we talk about the transmission line. As we know, the transmission line mainly works at the very high frequency. So at higher frequency, always we will do the field analysis. So in the field analysis, we need to understand the electric field and magnetic field orientation. Based on the electric field and magnetic field orientation, we can analyze the transmission line, such as waveguide transmission line, based on the mode TEM mode, TE mode, TM mode, and HEM mode. HEM mode, the hybrid electric magnetic mode, here we can say. So in further transmission line for the TEM mode, that is transverse electric magnetic mode. So as the name suggested, in this mode, the magnetic and electric field are purely transverse with respect to each other and with the axis of transmission line and the direction of propagation. If I consider direction of propagation in that z direction, so we have Ez is equal to 0 and Hz is equal to 0 for the case of transverse electromagnetic mode. For to have this kind of mode, there are some certain condition which need to verify. The first one is that there are at least two disjoint conductors in its cross section area, while the second one is the medium filling. The cross section is homogeneous, isotropic, and lossless media. So these two conditions we can have in the case of coaxial transmission line. As we know, the coaxial transmission line has two disjoint conductor. The first one is the inner conductor and the second one is the outer conductor. So and media filling inside the coaxial here. The media filling is by Teflon, that is the uniform media. That's why this transmission line verifies the two condition to have a TEM mode. That's why we can say the coaxial transmission line always has a TEM mode. This is the condition of the TEM mode. Now, the second one is the TE mode. TE mode is a transverse electric mode, while TM mode is the transverse magnetic mode. As name suggested, both modes are complementary by nature. If we say in terms of electric field, so either in terms of magnetic field. So, transverse electric field specifies it contains the electric field which are perpendicular to the propagation, perpendicular to the direction of propagation. So if I talk about the wave is propagating towards the z direction, so we have the transverse component of electric field, that is Ex and Ey will present, while Ez always be equal to 0. So by definition we can say for T mod Ez should be equal to 0, while Ez not always be not equal to 0. In the case of TM mode, if I talk about a magnetic field, as name suggests, transverse magnetic mode. So if we talk about if the propagation is occurring towards the positive z direction, so in that case the transverse component, that is that is x and y, will present for the case of magnetic field. So hx and hy will present, while hz should always be equal to 0. So while by the definition we can say hz should always be equal to 0, while ez is not equal to 0. In the case of hybrid mode, that is also known as HEM mode. So in this case, both TE and TM waves are coupled together and present simultaneously. In other words, we can say Ez is not equal to 0 and Hz is not equal to 0. Sometimes we can say this mode as a EH and HE mode, electric hybrid mode, and electric magnetic mode, magnetic and electric mode. So we can say HEM mode, hybrid electric and magnetic mode as well. Now the transmission line, planar transmission line, as this is a part of this microstrip line. So this planar transmission line is useful to have a small size and compatibility with IC technology as name. So here we can see two kind of transmission line. The first one is the strip line and second one is the microstrip line. So what is the difference between these two while looking the geometry point of view? So at the geometry point of view, you can clearly see here this is a strip, one strip. This is a cross sectional view of the transmission line. This is a strip, and this one is the this is a covering outer covering boundary surrounding the strip line. And this you can see here, this is a strip line, and surrounding media is different throughout the surrounding this strip width, strip line. So this is the difference between these two by looking the structure of these two transmission line. So you can clearly see here, as if we correlate this strip line with the coaxial cable, as we know that coaxial cable has at least two disjoint conductor. The first one is the inner conductor and second one is the outer conductor. If so similarly here we have two disjoint conductor. The first one is this strip line, and second one is the this outer conductor, this one and this one. So to have a TEM mode, the two conditions should be satisfied. The first satisfies the first one is the at least two disjoint conductor must be present, and the surrounding media surrounding media should be uniform. So the surrounding media from this to surrounding media from the this strip line is uniform, which is covering by the material epsilon r. So we can say this strip line always has the TEM mode. As we can clearly see here, this is the solid line is representing the E field and dotted line representing the magnetic field. So E field is towards the inner to the outer one, as we have in the case of coaxial cable, similar kind of a field distribution inside this strip line. That's why we can say this strip line always has a pure TEM mode, because this strip line satisfy the both condition, that is at least two distant conductor and homogeneous media surrounding the strip line. Now the second one is the microstrip line. So as you can clearly see here, the surrounding media through the strip line is not uniform, as downward toward the strip line is a different material from the upward side. So upward side is the air media and downward side is the dielectric media, which has the permittivity is epsilon r. So the first condition, that is to have a TEM mode, the transmission line should have at least two distant conductor, which is satisfied by looking this microstrip line as well. While the second condition, that is the media surrounding the strip line should be uniform, but while this microstrip line does not verify the second condition. That's why this transmission line doesn't have the pure TEM mode. It has the quasi TEM mode, because the second condition doesn't verify it. So that's why, as you can see here, the solid line is representing the E field and dotted line is representing the magnetic field. So solid line, so you can see here the some part of the electric field goes into the air, and this field is known as the fringing field, which is helpful in the radiation case. So as we can clearly see in this slide about the strip line, microstrip line. So you can clearly see here this field, upward side the velocity of phase velocity always be bp1 and phase velocity inside the dielectric media bp2. So these two phase velocity always be different, because the dielectric media of air is equal to 1 and this has certain value greater than 1, which is which changes the phase velocity of the wave. This is about the planar transmission line here. All the points I have covered in the last slide. I hope this transmission line, the microstrip line and the strip line is clear to all of you. Now because we have to design this microstrip line for a certain frequency. Suppose if I talk about if you need to design a microstrip line that has the impedance is 50 ohm. That's why you have to consider some certain parameter, and you need to understand how we can design the microstrip line for a certain impedance, that is 50 ohm, 60 ohm, 120 ohm, whatever you want to design. So this is approximate equation that helps to design a microstrip line. So this one is a effective relative permittivity formula, which has the which has the some certain parameter, that is W, D and epsilon, where W is the uh, uh, width of the microstrip line, while D is the thickness of the substrate and epsilon is the permittivity of the substrate. Uh, if I correlate this thing with the strip line, so this effective relative permittivity surrounding this strip line is known as effective relative permittivity, while all rest of the parameter will be same. So this effective relative permittivity has the formula like epsilon E is equal to epsilon R plus 1 divided by 2 plus epsilon R minus 1 divided by 2 into 1 by square root of 1 plus 12 d by w. Here d by w is the important parameter here. So and epsilon R is the relative permittivity here. So this effective relative permittivity always lie within the range of 1 and epsilon R. So if I find the relationship between epsilon E and W by D ratio, so if we increase the W by D, then what will happen? So W by D, if we increase W by D, so D by W will decrease and D by W will decrease, then this quantity will increase and epsilon R E will always be increase. So higher the W by D, lesser will be the value of fringing. Why we call lesser is the value of fringing? Because effective relative permittivity increases surrounding the media, all the electric field which is towards the air will confine mostly field is confined within the dielectric media. If the dielectric media value is increased, then most of the field confined within the dielectric media. So as in the first one, I can say higher the value of epsilon R, more concentrated will be the field inside the substrate. That will happen if you have the higher the W by D ratio. So this is the concept. What will happen if we increase the ratio of W by D, or if we decrease the ratio of W by D? Now approximate design equation for W by D is less than equal to 1 and W by D is greater than 1. So this is the characteristic impedance of the transmission line, which is represented by Z naught, right? So this is these two formulas are an empirical formulas which has been derived by using some practical by doing some practicals. This is an empirical, these are the empirical formulas. So initially Z naught is assumed. So W by D ratio, so for the case of W by D is less than 2, greater than 2, we have the different formulas, and here A and V are the constant. So these constant value is defined by these two equations, and this A is totally depend on the characteristic impedance of the transmission line and relative permittivity of the media, while the V's totally depend on similarly in the Z naught and epsilon R. So to have to design a microstrip line, we need to know the desired characteristic impedance and surrounding media permittivity. So next is the example where we have the dielectric constant, that is epsilon R is equal to 4 and thickness is equal to 1.6 mm. Design a 50 ohm transmission line that is equal to Z naught for the case of W by D. So all the things we know here, and only the we need to put these value in the in this formula. So by putting the value of epsilon R and Z naught, we have the value of V naught and A. So by putting all these value in the equation, we have W by D is equal to 2.92, which is greater than 2, and by using this equation we can have W is equal to we can have the width of the transmission line. This is W is equal to 3.28 mm. So this is the parameter we need to take to have the 50 ohm transmission line for the given parameter, right? So this is all about this example. So what is surface wave loss? All the transmission line, if I talk about the microstrip line has some losses such as surface wave loss. So surface wave loss is totally depend on the inhomogeneity of the media. If there is some discontinuity between two media, then we have some surface wave over the over the boundary. So for the microstrip line, there's two media. The first one is the air, and the second one is the dielectric media. So this is the joint, this is the boundary over which the surface wave propagate. To minimize the surface wave over the dielectric surface, we need to have a cutoff frequency of surface wave as high as possible. To make the cutoff frequency as high as possible, uh, we need to take the D as low as possible and epsilon s is as low as possible. So uh, we need to take the substrate thickness as low as possible and dielectric constant as low as possible to have the cutoff frequency as high as possible. So in the case of to have a less surface wave loss, we need to take low permittivity substrate and thin substrate, as I have mentioned in the next slide. And radiation loss can be minimized by using the high substrate and thin substrate as well, as you can see. Look at here, right? So I think this one is clear to all of you till now. Up to now, the mode symmetry. So you can clearly see here the diagram mention the even symmetry and mode symmetry. As the name suggested, even symmetry, which is if I take the half of it, then we have a same trend of electric field. While in the case of in this, we have a 180-degree phase shift in the E field. So we can say this one is the even symmetry with respect to the electric field, and odd symmetry with respect to the electric field as well. So I think this one is clear to all of you what is the mode symmetry. And this is a graph of effective relative permittivity versus frequency. As you can see, if we increase to if we move towards the high frequency, so at lower side of frequency, we can say the effective relative permittivity is less than the relative permittivity of the media. As we move towards the higher frequency, this effective relative permittivity matches with the relative permittivity of the media. So this is about the how the effective relative permittivity changes with respect to the frequency. So I think this topic, the microstrip line and strip line, uh, which uh, which uh, which is categorized inside the transmission line, is clear to all of you. So I hope this topic is clear to all of you. Thank you, everyone.